We are studying the various mapping procedures of cache. First, we studied the associative mapping cache. Then we studied direct mapping cache. And now we have to study the third type, that is the set associative mapping cache. If we again have a look on this associative mapping cache, we can see the structure was like this, and there is a disadvantage of this, which you can clearly see here, that for storing one word of data, you need to store a full address with that. That means, for example, if we see this example, in this example, we have a 12-bit data. For storing a 12-bit data in cache, we have to also store a 15-bit address. So in total, it will become, this cache word will become a larger word, which implies that the cost to store, cost per bit, storing one bit will be larger in this cache memory. And then the second is a direct mapping cache. In this is the direct mapping cache structure. In this, with the data, we only store the tag, not the complete address. A part of the address is stored here. So obviously this will be somewhat cheaper than the associative memory, this direct mapping cache. But again here we have a disadvantage. What is that? And for example, we have an address of 00000, 5 zeros. So this can be seen, it is stored here with an index of 000. The last 3 bits is 000, and the tag, which is these first 2 bits, it is here. So the corresponding data 1220 is in cache. It is in main memory, and a copy is also in there in cache because the CPU has used it. Now, if the CPU wants this address 01000, then it cannot be moved to some any other place. It has to be put here because the index is matching. So then we have to replace this 1220 by 3450. After some time, if the CPU wants 02000, this thing, then again the 3450 here will be replaced by 5670. And we see that if the CPU continuously asks for such locations, the hit ratio will automatically go down because there will be many misses. We have to do continuously replacements here. So in this direct mapping, in such a scenario, the hit ratio will go down. One of the simple ways to solve this problem is that why not increase the size of this column wise cache memory and store more tags here. So here we can store tag 00 in the corresponding data. Why not to put here tag 0 space for tag 01 and the corresponding data, and so on, so that more tags in corresponding to index can be found. That we can see here in set associative mapping. So this is the structure of a set associative mapping cache. So very similar to this direct mapping, but extra things are added here. So we have an index. Corresponding to that index, there is a tag and data, and in the same row there is again tag and data, and it may continue depending on the structure of the this thing. And this structure is called a two-way set associative mapping cache. Two-way because there are two data entries in a single row of cache. If we put a third here, then we will call it three-way, then a four-way, and like that. This is two-way because there is a binary, a two pair. There are two pairs, tag and data and tag and data, two pairs. Okay, what will happen here? So if I have an address of CPU produces an address of 0 1 0 0 0, that can be found here. If the CPU says 0 2 0 0 0, that can also be found here. Then if the CPU says 0 3 0 0 0, that will not be found here. Then one of these has to be replaced with that thing. And for replacement purposes, replacement occurs only when the index is same but the tag is not matching. So if the CPU says 0 3 0 0 0, we can see 0 0 0 is here but 0 3 is not here. So we have to do a replacement. Someone has to move out and 0 3 will come at his place. But which one should move out, whether this one or this one, that is decided by some algorithm. For example, one of the algorithms is FIFO, first in, first out. So the pair which came first will go out and the new one will come in. That means that if at, for example, at a certain time, 10, for example, at 10 this has come in, and at 11 this has come in. I'm giving this example for the sake of understanding. So if this has come in at 10, this has come in at 11, then this is the first thing, and that means 0 3 will be this will go out and 0 3 entry will come here. So first in, first out. In the same way, there is another algorithm that we call as LRU. LRU means least recently used. First is FIFO, another that may be used is LRU, least recently used. So, which means that whichever of these two has been least recently used will move out and a new one will come in. Okay, least recently used means we don't have to see when it came in the memory, we have to see when it was used. So for example, this thing was used uh, at 10 and this was used at 11, and then again this was used at 12, then which is the least recently used. So the least recently used will become this. Least recently used means which has not been used for a good amount of time. So among these two, which has been least recently used, this, because this was used at 11 and this was used at 12, right? So this algorithm works in such a way that it sees which is the least recently used and the replacement occurs accordingly. So this is set associative mapping cache. Let us see another topic. The topic is writing into cache. So what is that? We say that when we have to read, when a CPU produces a read operation, asks for a read operation, there will be a search in cache. If it is found there, it is a hit. If it is not found there, it will be a miss, and reading will happen from RAM and like that. But if the CPU wants to write something, CPU wants to write some data or instruction into the memory, how will that happen? There are two ways of writing. One is called write through method, the another is called write back method. Write through method means that if the CPU wants to write something at certain location, writing will be done at both places. The main memory will be updated with that data. That data will be written in main memory, and if the copy of that data is in cache, parallelly, simultaneously, the cache will also be updated. So it depends whether the data has a copy in cache or not. And if there is a copy in cache, then the writing will be done at both places, in cache as well as in the RAM, in the main memory. So this is called a write through. We are writing through both simultaneously. There is another write back method. What is that? That whenever the CPU wants to write certain thing, that thing, if that is present in cache, it will, the cache will be updated. So during that operation, only the cache will be updated. It's another copy, the original copy that is in main memory will not be updated, but there will be a flag that will be set, it will be marked, so that we know that a change has occurred. And later, when the word is removed from the cache, then only the copy of the main memory is updated using this value of cache. So this method has one advantage, that if the change of the contents of that cache at that location happens many times, the RAM is not continuously updated. It is only updated when the word moves out of the cache. So it is somewhat a time saving procedure. You don't have to write into this main memory if there is a change in cache. You only have to write in main memory when there the word is removed from the cache because of some replacement or some other reason, then it will happen. So this is called the write back method. Let us take a numerical problem which is related to set associative mapping. So the problem says a two-way set associative cache memory. So it is given that it is a two-way. That means the cache memory will have a tag data in one row, and it is given that it uses blocks. So it is also using now blocks. So its rows are divided into blocks like that of direct cache, and each block is of 4 words. So the total number of rows that are there in the two-way set associative cache, they are again divided into parts. Each part is called block, and each block is given that it is of 4 words. In other words, every 4 rows constitute one block. Okay, then it is given that the cache can accommodate a total of 2048 words from main memory. So what is the capacity of cache? It is given that from main memory 2048 words of main memory. In other words, 2048 data words will can this cache accommodate, can it store. And the main memory size is also given 128K into 32. The question A part says formulate all pertinent information required to construct the cache memory. So whatever information we need to construct this cache, just collect that, formulate that, and also tell what is the size of the cache memory. Okay, so in the solution we'll see, first of all we will see what is the size of main memory. The size of main memory is given 128K into 32. Two things we can easily deduce from here. So for first thing is, what will be the address bits, CPU address bits, how many bits will be there in the address. The address line will contain obviously log to the base 2 128K, this thing bits. So which comes out to be 17. That means the address that the CPU will generate, the address will constitute of 17 bits. The second thing given here is 32, which means that the data bits are 32. The data is of 32 bits, or the word length of main memory is 32 bits. Okay. Now, first part says get the information to construct the cache. So to construct the cache, what main things we need? We want to know what is the size of tag, the index, and how is the index divided, and structure of the cache. So let us find those things. So first thing, we have found that the total address is 17 bits. It can be found through the size of main memory. So this is the number of rows in main memory, which implies the address bits will be 17. Okay, now the question itself says that this cache memory can accommodate 2048 words from main memory. So the question says that 2048 words of main memory can be stored in cache. Since we know that this is a two-way set associative cache, which implies that two words are stored in one row of cache. That's why it is called two-way. So two words of main memory are stored in one row of cache. So how many rows of cache will be in their total? The number of rows in the cache will be 2048 by 2. This 2 came from here, two-way. Since in one row of cache, two words can be stored, how many total rows will be there? 2048 divided by 2. So the total rows in the cache will be 1024. So like this. So this is a two-way set associative cache. Two-way, so it is tag data, tag data. How many rows are there? 1024. How many words in total will be stored? One word here, one data here, second here, third here, fourth here. Obviously the total will be 2048. Okay, now since the this number of rows in this cache memory is 1024, what will be the size of index or the address of this cache? The address of this cache, which we also call as index, will obviously be log of 1024. So the cache address bits, which we also call as index bits, will be log of 1024, which is 10. So we have found the index bits, it is 10. So out of these 17 address bits, 10 are for index. So automatically the remaining will be for tag, which will be 7. 17 minus 10 is 7. Since the question also says that this memory is divided into blocks, cache memory is also divided into blocks. That means the index will further be divided into block and word bits. So we have to find these two also. So we will write that the question says that each block has 4 words. So if one block has 4 words, to address 4 words, we need 2 bits. So if we have 4 things, for addressing 4 things, we need 2 bits. That means 2 bits are required for one block. That automatically means the number of bits in this word is 2. So this word will be 2 bits, and if this is 2, block automatically will be 8 bits. So the index 10 will be divided into 2 parts. Word is 2 bits and the block is 8 bits. Then the B part is there, which says what is the size of the cache memory. So the size means how many rows and how many bits in the column in each word. So we need to see from here, starting from here up to here, what is the total number of bits. So the width of the cache, what is the width? The width is equal to, that means one row of cache contains tag plus data plus tag plus data. So we have already found tag is 7 bits, data is given 32 bits. So tag 7 plus 32 plus 7 plus 32, which is equivalent to 78. So that means the width here is 78, the height or the number of rows is 1024. So the size of cache memory will be 1024 into 78. Thank you.